So we're going to look at logarithmic functions. Before we do that, does anybody remember what an inverse is? How do you find the inverse? Switch x and y, try to solve for y, right? So if I'm trying to find the inverse of this graph, y is equal to 2 to the power of x, I'm going to switch x and y. And then I want to solve for y. What happens? Can you solve for y? You don't know enough math to solve for y right now, okay? That's why we introduce logs. You cannot solve for an exponent, right? In certain cases, if I gave you 10 and 100 and said, and did that, you could guess and check, right? And you'd come up with 2, right? 10 squared is 100. So in certain cases, you can do it with guess and check. Stuff like this, you cannot guess and check, okay? So we cannot solve for y. All right. Now we're going to go back to the graph of y is equal to 2 to the x, and we're going to look at it graphically with the inverse. The graph y is equal to 2 to the power of x is an exponential graph that is growth or decay. Growth, y-intercept of 1, and a horizontal asymptote of, has it been moved up and down? Is there a k value? So it's 0, right? So we can sketch that graph. So it has and it looks like this. I'm not doing the table values. We're just gonna, whoa, that's really bad. But it'll work. If we do the inverse of that, okay? So let me mark the horizontal asymptote. We'll do it in orange. Here's our horizontal. Okay. Now, if we do the inverse, we switch the x and y values, right? And then sketch the graph. So 0 and 1 becomes 1 and 0. And these points, remember, can reflect across the line y is equal to x, right? That's another way of doing it. Everybody agree with that? So if they reflect across that line, you get this graph. This is x is equal to 2 to the power of y, because it's the inverse graph. Is everybody okay with that? All I did was sketch the inverse of y is equal to 2 to the power of x. Yeah? One. Is that one? Oh, I drew it. Pretend that's 1. Sorry, I didn't look. Yeah, you're right. They go up by 0.5. Sorry. 1. Just say that that's 1, 2. Okay, so all I did was sketch the inverse. This inverse graph is a logarithmic graph. The inverse of the exponential function is of the log. Okay. This is a logarithmic graph. And that's what we're going to look at. We're not going to look at the graphs, but the key point here is the inverse of the exponential is a log. So if you flip the page, that's what it's going to say, okay? All right, so the next page. This is the definition of a log, the inverse of the exponential function, okay? It's good to remember that. So when we were doing it algebraically, we got to this point, x is equal to the power of y, and then we got stuck. We couldn't solve for it. Logs allow us to solve for it. And you rewrite it, and I know this is totally new, so we're going to practice doing this because it's very important. X is equal to 2y becomes y is equal to log base 2 of x. This 2 here is your base, just like it's the base here. Okay? Different bases for log. So now we solve for y. Y is equal to log base 2 of x. So this leads us to the log function. X must be greater than 0. In other words, you cannot log a negative number. Okay? Cannot log a negative number. Now we can tweak it so that we can put negative numbers in, but when you actually go to hit your button, it'll always be a positive number. So we can shift it left and right. We'll look at that later. B, just like in exponential graphs, B has to be positive. And have a negative base. And B cannot be equal 1. That's tied up with the definition of a exponential graph. So I'm not going to ask you this. You do need to know what the base of a log is. The number that you're logging, this x value, is called the argument. If you remember that, great. If you don't, it's not a big deal. Okay. All right. So this graph here, x is equal to 2 to the power of y, which we just did in the previous page, is the inverse. That is, nobody would ever write that. They would write log base 2 of x. That is what the graph is. Now, because they're inverses of each other, we know some information about this log graph. So first of all, y is equal to 2 to the power of x. What's the domain of the exponential graph? Are there any restrictions? No, so it's XER, all real numbers. What is the range of the exponential graph? Greater than 0. What's the x-intercept of this graph? Oh, that's the y-intercept. X-intercept is none, doesn't hit the x-axis. Y-intercept is 0 and 1. Asymptote is y is equal to 0. That's exponential graphs 101. Okay. What happens when you do the inverse to the domain and range? They switch. So the range becomes the domain. So the domain is x is greater than 0, which is, you can't log a negative number. The range becomes all real numbers. What's the x-intercept? 1 and 0, because you switch the points, right? So it's 1, 0. Y-intercept, is there any? Nope. Now, if we had a horizontal asymptote for the original, and we do the inverse, what are we going to get? You're going to get a vertical asymptote. So the asymptote is a vertical, and it's x equals 0. And if you look at this graph, this log graph will never touch that. Unless you shift it left or right, which you can do. We might do that later on. Okay. I just need you to be familiar with what a log graph looks like, okay? We'll talk about that later. The real important part for today's lesson is converting between what's called logarithmic and exponential form. And that's what we're going to do right now. So if we have, let's fill this in, 2, 1, 0, that equals 2. Okay. Obviously, when you have a log written in the equation, it's the logarithmic form. When it's written without the log, it's called the exponential form because you have an exponent. All right? Remember, this little number here is called the base. All right? And the base, when you're writing exponents, is the number raised to whatever the exponent is, right? So the base in every one of these is 2, 2, and 2. So I'm just going to put a 2, a 2, and 2. And when you're converting from logarithmic form to exponential form, you have an expression like this that equals number. The base moves over, and this number moves up to the exponent. This is the exponent. Okay. When you convert to exponential. So if I'm writing log base 2 of 4 equals 2, and I want to write it in exponential form, I'm going to write 4. The 4 stays the same, the argument. And this 2 moves over here and kicks that 2 up to the power of 2. It has to make sense mathematically. 4 is equal to 2 squared. The next one, I'm going to write what? What's going to happen to this 2 here? It moves over, kicks that up. So that 1 goes up there, and this 2 stays there. 2 is equal to 2 to the power of 1. What's my next one going to say? There you go. 1 is equal to 2 to the power of 0, which makes sense, right? Okay, on the other side, now we're going to go from exponential form to logarithmic, going the other way. You have to be able to go back and forth. So when you're in exponential, that is your base, right? Because it has the exponent on it. That becomes the little subscript. It's not, don't write this, don't write log 2 of 1/8, don't write log 2 1/8 equals 2. That means something different. You have to write this, and people will get lazy and it works out at the beginning. Again, because you will get confused when we start doing more complex examples. Not to write like this. You need to write it as a subscript, a little number just below the log on the G. Log base 2 of 1/8. That's what you want to write. Okay? So the 1/8 is the argument, right? It doesn't change. You write log of your base, and what happens to the exponent is it falls down. And that doesn't equal 2. It should equal 3. The exponent falls down. It just becomes a regular number. And that's the power of logs, is they bring the exponents down so that then you can use algebra on them. Okay? When it's written like this, it's hard to use algebra on it. Okay? But when you bring the 3 down, bring the exponent down, especially when it's a variable, you can start to use algebra on it. So this next one, log, what's my base? This 2. So little 2. Then what? What do I write? 1/4 equals -2. What about the next one? Log, what base? Of equals, there you go. Okay. Can you write that in logarithmic form? What's your base? I just want you to write it as a log. So what is my base? It's 10, right? So I can go log base 10 of what number? 1,000 equals 3. What about this? Log base 5 is 625 equals 4. Can you write it in exponential? So go the other way. What's my base? 5. So the 625 stays there, equals 5 to the power of 4. And the 4 gets kicked up to become an exponent. Is that okay? All right, we're going to practice it some more to the next page, just because it's so important. You have to be able to just do it. Don't worry about the graphing stuff. We can look at that later. We're not doing that. We're doing these two. All right, this will be the last bit for the day, and then I'll just give you some time to practice. Yeah. We're going to write each of these in exponential form. So the first one, what is my base? 7. So it should be x is equal to 7 to the power of 4. What's the second one going to be? Exactly. 15 is equal to 5 to the power of y. So that moves over there. That's really what you're doing. This base is moving over here and kicking up that. So in this one, we're going to get t to the power of m is equal to b. With that 4 in front of it, right? You need to make it look like these things first. So divide off the 4. So then what does it look like? B to the power of 5 over 4 is equal to 6. And last ones for the day. We're writing them as a log. So what's my base in A? 4. So 3, the exponent falls down, is equal to log base 4, 64. Oh. Second one, excuse me, -3 is equal to log base 2 of 1/8. What's C? Log base E of F is equal to D. Or D is equal to log base E of F. Final one. Log base A of 2x plus 4 is equal to 5. Are we okay with that? All right. Just do 3 and 4, please. It's taking way less time. I might do one more mini lesson since we have time. So 3 and 4 is just practicing what we just did. Oh. Okay, bottom of page 225. This will not take long. It's just one more little thing we're adding onto it. So what's the difference between all of these and what we were just doing? Or we were looking at stuff like this. Y is equal to 3x, and I was asking you to convert to logarithmic form. What's the difference between all these? And this. Yeah, there's an a value, right? All you have to do is get that off. You have to have this side equaling just the exponent, right? We don't want an a value there. So you must divide off that a value. So the first one, divide off the 2, and you get 3 to the power of x. And then convert to logarithmic form. What's my base? 3. So it becomes log base 3 of y over 2 is equal to x. Second one, divide off the 7. My base is 4. So everything is the same. Once you get that a value divided off, it's the exact same thing. Okay? What about d? 3/2. If you divide by 3/2, what do you get? 1 over 3/2 is the same as 2/3, right? because I can multiply the 2 up and divide off the 3. So I'm going to get 2y over 3 is equal to 10 to the power of x. And log it. So base 10. Sometimes if it's complicated like that, I'll put it in brackets, but you don't have to. Equals x. Okay. Here we're just going to solve for y essentially. So how do I solve for y? My y is all tied up. I need to get rid of the log. So you're going to convert to exponential form. So my base is 7 on the first one. That moves over, kicks up the x. So now I've got y over 3 is equal to 7 to the x. How do I solve for y? Multiply the 3 over it. So it's y is equal to 3 times 7 to the x. Can I write 21x? No, just leave it, because they're not the same base. Same for this one. Convert to exponential. Y over 4 is equal to 10 to the power of x. Multiply the 4. 4 times 10 to the power of x. Getting the point? All right. That's it. Please do 8, 9. No, not 8. 9, 10, and 11, please. And if you're feeling ambitious, try 12.